Welcome back to the study of rational function. We continue with the investigation of the end behavior of rational function. Recall that again, a rational function is a ratio of two polynomials, p over q, and say p is a polynomial of degree m, and q is a polynomial of degree n. The coefficients are respectively a sub 0, a sub 1, a sub m, and b sub 0, b sub 1, b sub n, where, because the degrees are m and n, necessarily the leading coefficients are not zeros. For instance, if the leading coefficient here was 0, it would follow that the degree actually is less than n. All right, we mean to look at this ratio, and in looking at this ratio, we want to perform a simple algebraic manipulation, which will be the following. We want to compute the limit of this expression when x goes to infinity. That's what it means to study the end behavior. So the idea is this. We factor out x to the power m in the numerator and x to the power n in the denominator. In the numerator, in parentheses, we will have a sub m plus a sub m minus 1 times 1 over x plus etc. plus a1 1 over x to the power m minus 1 plus a sub 0 times 1 over x to the power m. And in the denominator, we will have a similar construction, x to the power n, bn plus bm minus 1 times 1 over x plus etc. plus b1 1 over x to the power n minus 1 plus b naught times 1 over x to the power n. Now, x to the power m over x to the power n is x to the power m minus n, and the rest of this construction stays. So this will be x to the power m minus n times the rest. Now let us for now concentrate on expressions in the parentheses. And remember, x goes to infinity, so in particular 1 over x in any positive power goes to 0. When x is a huge number, 1 over x is a small number. 1 over x squared is a small number. 1 over x cubed is a small number, and so on. So all of these circled expressions approach 0 as x approaches infinity. Now, what about x in the power m minus n? Well, it all depends on the sign of m minus n. And there will be three cases. For instance, what if m equals n? If m equals n, m minus n is 0, and x in the 0 power is simply 1. And then we get the ratio a sub m over b sub m, because all of these are zeros. Now, if m is greater than n, so m minus n is positive, x to the power m minus n, which is x in the positive power, will always be an infinitely large quantity. And it doesn't really matter that these go to 0, because the fraction always goes to a sub m over b sub m. The fraction always approaches the ratio of the leading coefficients. I should probably simplify my writing and say that explicitly. The fraction approaches a sub m over b sub n, which is the ratio of the leading coefficients. So, where the whole expression goes depends on the sign of m minus n. If m equals n, so m minus n is 0, this is 1, and we get that the whole expression approaches 1 times the ratio of the leading coefficients. Right, a sub m over b sub n, but because m equals n, that simply is a sub m over b sub n. If m is greater than n, so m minus n is positive, it doesn't really matter what the ratio of the leading coefficients is. It's some finite number, which is non-zero. I should say that. And whatever that non-zero number is, multiplied by an infinitely large quantity, we still get an infinitely large quantity. And if m is less than n, x to that power will be a quantity that's infinitely small. Why? Well, because x to the power m minus n is 1 over x to the power n minus n. And if m is less than n minus m is positive. X being huge, raised to a positive power is still a huge quantity. 1 over a huge quantity is a small quantity. So x to the power m minus n, in case when m is less than n, will approach 0, and multiplied by the ratio of the leading coefficients, it'll still be 0. We obtain this very important result, that the ratio of two polynomials behaves at infinity either as the ratio of the leading coefficients if the powers of the polynomials in the numerator and the denominator are equal, or simply approaches 0 if the degree of the numerator is less than the degree of the denominator, or is infinity if the degree of the numerator exceeds the degree of the denominator. In particular, in these first two cases, we have a horizontal asymptote. Recall that a horizontal asymptote occurs if and only if the limit at infinity of your function is a finite number, 0 or not 0. Right? By definition, the horizontal line y equals b is a horizontal asymptote if a limit of f at infinity equals b, whether b is 0 or non-zero. That's what this theorem says. We have a horizontal asymptote in the two special cases when the degrees of the numerator and denominator are equal, or when the degree of the top is less than the degree of the bottom. In the first case, we have a horizontal asymptote y equals b, where b is the ratio of the leading coefficients. And when the degree of the top is less than the degree of the bottom, the asymptote is simply y equals 0, which is the horizontal axis. All right. This here is an important comment. We already said before that it's perfectly fine if the graph of a function crosses its own horizontal asymptote. In fact, it could do that infinitely many times. There is no contradiction here. And let's examine the graph of this function, x over x squared plus 4x minus 5. Let's in particular compute the limit at infinity. Such limits are easy to compute if you factor out the highest power of x in the top and in the bottom. Well, the highest power of x in the numerator is just x, and in the denominator we can factor out x squared, so that in parentheses we have 1 plus 4 over x minus 5 over x squared. When we cancel this x and x in the denominator, which is permissible because x goes to infinity, and in particular, it's safe to assume that x is not 0. we end up with a limit as x goes to infinity of 1 over 1 plus 4 over x minus 5x squared times x. Let me write it in a slightly different way. I can write this as 1 over x times 1 over 1 plus 4 over x minus 5 over x squared. 1 naturally goes to 1, 4 over x goes to 0. As x goes to infinity, so does 5 over x squared. So this whole second fraction goes to 1 divided by 1, which is of course 1. But now there's 1 over x, where x is huge. When x is huge, 1 over x is small. So small times 1 is small. So it means that the graph of this function has the x-axis as a horizontal asymptote. Now we look at certain special cases of that big fact that we just established about the limits at infinity of rational functions. Remember, it's either the ratio of the leading coefficients or 0 or infinity. So the special cases are the following. Suppose the top and the bottom have equal degrees. As we know, we have established this, the limit of the quotient at infinity simply is the ratio of the leading coefficients. And the graph will have a horizontal asymptote, y equals the ratio of the leading coefficients. Here is one example of this situation. Let's work with this function, 3x squared plus 2 over x squared plus 4x minus 5. We see immediately that the numerator doesn't factor over real numbers. The polynomial 3x squared plus 2 simply has no roots over real numbers. But the denominator x squared plus 4x minus 5 easily factorizes as x minus 1, x plus 5. So we see that because 1 and negative 5 are the roots of the denominator, but not the numerator. The vertical lines x equals 1 and x equals negative 5 are vertical asymptotes of f. And indeed, we see that in the picture, x equals 1 and x equals negative 5 are vertical asymptotes of this graph. I always recommend that you compute one-sided limits at your vertical asymptotes. Say, for instance, let's work with the vertical asymptote x equals 1. Let's compute the limit at 1 from the right of f and from the left. So we know the limit will be infinity. We know that because that's a vertical asymptote. The question is, what sign will that infinity have? Well, x approaches 1 from the right, which means x is greater than 1, which means x minus 1 is positive, but close to 1. If x is a number that's close to 1 but greater than 1, then this is always positive, this is also positive, and this is also positive, because that number will be close to 6. So the entire fraction then will be positive. And the limit at 1 from the right is positive infinity. That's a valuable piece of information. It could have been like this, but now we know that the limit is positive infinity, so we know the graph goes like this. Likewise, we compute the limit at 1 from the left. We see immediately that once x minus 1 is negative, and this is true because x is less than 1, we have this portion positive, and this factor negative. So the entire fraction will be negative. So the limit is negative infinity. And that's exactly what we see in the picture. Likewise, we can do this work for the other asymptote, -5. A limit from the right at -5 is clearly positive infinity. That is because x is slightly greater than 5 implies this number is positive, this number is positive, and this number is always positive. Now, x is less than -5, which makes this factor negative. This factor is positive. Once again, x is less than -5, which means this factor is negative. This factor is negative. This factor is roughly -6. This factor is positive. So this is positive infinity. Let's check the previous answer. X is greater than -5, so x plus 5 is positive, this is roughly -6, so this is negative. This is positive. So the entire fraction is then negative. And again, even if we didn't have this picture on the left, we could have obtained all these results just from computing the limits. Finally, let's compute the limit at infinity. Now it's easier if we look at the non-factored form, x squared plus 4x minus 5. We see that the degree of the top equals the degree of the bottom. Both are of degree 2. And so, in this case, the limit of the ratio is simply the ratio of the leading coefficients, which are, of course, 3 and 1. Which immediately implies that y equals 3 is a horizontal asymptote. Which is exactly what we see in the picture. Note, by the way, that here the graph actually intersects with its own horizontal asymptote. We couldn't derive this from our work. It's perfectly fine if the function went this way. Our analysis doesn't show that the graph will intersect its own asymptote. All right. Now, another special case occurs when the degree of the numerator, p, is exactly one more than the degree of the denominator, q. In this case, we will have what's known as the oblique asymptote or slant asymptote. The asymptote is neither vertical nor horizontal. It will be a straight line, kx plus L, where slope k is determined as the limit of the ratio p over x times q, and y-intercept L is determined as the limit of the expression p over q minus kx, where k is the slope. Let us work with the example. In this example, we have precisely that situation. The degree of the top is one more than the degree of the bottom. The degree of the top is 2, the degree of the bottom is 1. And so, to compute k, I could consider the limit as x approaches infinity of the ratio 3x squared minus 2x plus 1, that's p, over x times qx. That is x times x minus 1. Now a little algebra. We see that now we have the ratio of two polynomials of equal degrees. Both are of degree 2. And as we know, the limit in this case is simply the ratio of the leading coefficients, 3 and 1. So k equals 3. And now to find L, all you need to do is to compute this limit. P over q, 3x squared minus 2x plus 1 over x minus 1 minus k times x. K is 3, so that's 3x. Now we need a little algebra. We see that 3x squared and negative 3x squared cancel out. And when we combine the like terms, we have 3x minus 2x. That's x. The free term is 1. And now we have a ratio of two polynomials of degree 1. Both have leading coefficients 1. So the limit is the ratio of the leading coefficients, which is 1. So we have established that the line y equals 3x plus 1 is an oblique asymptote of our function f. Note, by the way, that x equals 1 is a root of the denominator, which is not a root of the numerator, because the numerator at 1 is 3 times 1 squared minus 2 times 1 plus 1. That's 3 minus 2 plus 1. That's 2. That's not 0. That implies that x equals 1 is a vertical asymptote. And indeed, all our findings are confirmed by the graph on the next page. X equals 1 is a vertical asymptote. Y equals 3x plus 1 is an oblique asymptote. The graph approaches the asymptote. In general, when the degree of the numerator is more than 1 greater than the degree of the denominator, there could be curvilinear asymptotes. For instance, this graph could be approaching a parabola, not a straight line. But we won't look at such cases, although they might appear in your homework. And another special case is when the degree of the numerator is strictly less than the degree of the denominator. As we know, in this case, the limit is 0, and we will have the horizontal asymptote y equals 0, which is the x-axis. Here is one such example. Let's work with this function 4x plus 2 over x squared plus 4x minus 5. Let's factor both the top and the bottom. Well, I can factor out 4, so that'll be x plus 1/2. Which implies that x equals negative 1/2 will be might be an x-intercept. I'm saying might be because I haven't yet checked that negative 1/2 is not the zero of the denominator. If it's a zero of both the numerator and the denominator, it will be a point of removable discontinuity. And the denominator factors as x minus 1 root times x minus the other root. And what are the roots? The roots are 1 and negative 5. So we see immediately that x equals 1 and x equals negative 5 are vertical asymptotes. Indeed, that's what we see in the picture. Let's again find the one-sided limits. It's good practice. At 1 from the right, this will be positive, this will be positive, and this will be positive. So the limit is positive infinity. At 1 from the left, now x minus 1 is negative. X being roughly 1 makes this positive and this positive. So the entire fraction is negative. That's what we see in the picture. On the left, it's negative. On the right, it's positive infinity. Now at negative 5. At negative 5 from the right. X is roughly negative 5. Makes this negative, and this positive. So the entire fraction is positive. And you can check that on the left, it will be negative, because this is now negative, this is negative, and this is also negative. So the entire fraction is negative. What about horizontal asymptotes? What about horizontal asymptotes? Well, we compute limit of f at infinity. And we see immediately that because the degree of the denominator is strictly greater than the degree of the numerator, the limit, as we know, is 0. So that implies that y equals 0, which is, of course, the x-axis, is a horizontal asymptote, which is what we see in the picture. It should be noted that for rational functions, a horizontal asymptote, if it exists, it is necessarily unique, because when do we have horizontal asymptotes? We have horizontal asymptotes precisely in these two cases. Well, either the limit is the ratio of the leading coefficients or 0. In any case, the limit is unique, so the horizontal asymptote, if it exists, is unique. But of course, there could be vertical asymptotes that are not unique. This example has 2 vertical asymptotes. In general, there will be as many vertical asymptotes as there are zeros of the denominator that are not zeros of the numerator. And at the end of this topic, we look at 2 sketching examples. And before we solve them, let us maybe write a quick summary or a quick to-do list that you might want to follow when you need to draw the sketch of a rational function. Our function, as always, will be p over q, where p and q are polynomials. We keep the same notation. The first and foremost, you need to factor completely over real numbers both the numerator and the denominator. Factorize p and q over real numbers. Don't find complex roots. Well, when you factorize them, the factorization will be some constant, let's call it constant 1, times x minus a1, x minus a2, x minus am, times some polynomial p1, we'll explain what they are, over also some constant, let's call it constant 2, x minus b1, x minus b2, x minus b. I shouldn't be using letters a and b because I was using them for coefficients. So let me rewrite this. Let's say in the numerator we have x minus alpha 1, x minus alpha 2, x minus alpha t times p1 of x. And in the denominator we have the factorization x minus beta 1, x minus beta 2, x minus beta s times q1 of x, where the polynomials p1 of x and q1 of x have no roots over real numbers. So that these polynomials cannot be factorized any further. You find all roots, whatever the roots of p are, they are alpha 1, alpha 2, alpha t. p1 has no roots. And the same in the bottom. beta 1, beta 2, beta s are the only roots of q. Polynomial q1 has no roots over real numbers. Now, how do you find this factorization? Very often you will use the rational root theorem. Then you would use polynomial division, and again the rational root theorem, and again polynomial division. Here we, of course, assume that the alphas and the betas are all real. We don't factorize over complex numbers. The numbers alpha 1, alpha 2, etc., alpha t, beta 1, beta 2, etc., beta s are real. The second step, identify vertical asymptotes and points of removable discontinuity. Where will we have our vertical asymptotes? Our vertical asymptotes will occur precisely at those betas which are not roots of p. If the numerator p at some point beta I is not zero, then the vertical line x equals beta I is a vertical asymptote, because that beta I is a root of the denominator, but not a root of the numerator. Here I is an index from 1 to s. If, however, p at beta I is 0, then that point is a point of removable discontinuity. In particular, remember that warning again. Not every root of the denominator q is a vertical asymptote. Only those roots are that are not roots of the numerator. We saw examples where the denominator and the numerator share a root. Such points are not vertical asymptotes. I would also add here, compute one-sided limits. At vertical asymptotes. It helps a great deal to understand the behavior near vertical asymptotes. Step 3. Identify horizontal and oblique asymptotes. Or lack thereof. They don't have to exist. By computing the limit at infinity. or in the case of oblique asymptotes, by computing limits p over xq, which will be the slope of our oblique asymptote, and the limit p over q minus kx, which will give you the y-intercept of your oblique asymptote. An oblique asymptote occurs if and only if the degree of p is 1 greater than the degree of q. The next step is to identify the zeros. What are the zeros of f? Well, the zeros of f are all those alphas that are not roots of the denominator q. X equals alpha j is a root of f if and only if q at alpha j is not 0. In other words, if and only if alpha j is not equal to any of the betas. J here from 1 to s. Correction, from 1 to t. Also here, identify the behavior at zeros. The behavior could be either crossing, as we know, or touching. Let's write our factorization in a slightly different way. If we add powers here, we can assume that all the alphas are distinct. So I can add powers here. Maybe use letters M1, M2, MT, and the same here. N1, N2, and S. So suppose some alpha is a root of f. It's a root of the numerator, but not the root of the denominator. How do you determine if it'll be a crossing or a touching? It depends on the parity of the corresponding power. If, say, alpha j is a root of f, then it is a crossing if and only if the corresponding power mj is odd, and it is a touching if and only if the corresponding power mj is even. We should add here that all m1, m2, etc. mt, and 1 and 2, etc. ms are positive integers. Also, we should add that all alphas are distinct. All alpha 1, alpha 2, etc. alpha t are distinct, meaning no two are equal. And all beta 1, beta 2, beta s are distinct. All right, so we said how we determine whether a root is a crossing or a touching. And the last step, you probably want to compute y-intercept, unless your function is not defined at 0, and maybe the value of your function at some other points. Okay, what's left to do is to look at these two examples. Let me maybe do this in a separate video. Thank you.